Alright, in this section we are going to be talking about isotopes. Now before we get into what an isotope is, I've got to do a couple little reminders here. So quick reminder, all atomic nuclei are actually made up of protons and neutrons, except for the simplest type of a hydrogen atom. Because the simplest type of a hydrogen atom, which is also the most common, only has one proton. Okay, so if you remember, the number of protons actually determines the element of the atom. So one proton is a hydrogen atom. Okay. Now, hydrogen atoms generally, again, most common form just has the proton, doesn't have any neutrons, but there are a couple different types. Okay, so you can have a hydrogen atom that has one neutron and one proton. Okay, so again, the one proton determines that it is a hydrogen atom. The one neutron is just kind of hanging out with that proton. Okay, so when you have one neutron and one proton, okay, you have a mass number of 2 because each neutron and each proton has the same mass number, 1. So you add those two together, you get 2, and so it's called deuterium. Okay, one neutron, one proton. If you go up to 2 neutrons, okay, so this is incredibly rare, plus one proton. Again, one proton means that you have a hydrogen atom, but because you have 2 neutrons and one proton, now you have a total mass number of 3. So it is tritium. Okay, so just kind of special little name for a rare atom of hydrogen. So a proton has a positive charge, which is equal in magnitude to the negative charge on an electron. Okay, so even though the electron doesn't have mass compared to a proton, it does actually balance out the charge. So the nuclei, or the nucleus of an atom, of different elements, differ in the number of protons. They can differ in the number of neutrons, don't necessarily have to, but they have to differ in the number of protons if they are different elements. And again, the number of protons determine the atom's identity, determine what element it is. Alright, so now we're going to talk briefly about some of the forces in the nucleus. Okay, so you have what's known as the electromagnetic force. So that is the force of attraction or repulsion between electrically charged particles. Okay, so if you have two similarly charged particles, they will repel each other. They will try to force each other away. If you have opposite charges, they will try to attract each other and pull each other back together. Okay, so electrons will stay in the area around the nucleus because of those electromagnetic attractions between the positive nucleus and the negative electrons. Okay, so that's what keeps them moving, kind of falling around the nucleus in a way. Okay. Now you also have the nuclear force. So the nuclear force is an attractive force between the quarks inside the subatomic particles of a nucleus. Okay, so we don't really talk about quarks too much. They get really kind of weird, okay, because they are smaller than protons and neutrons and actually will make up those subatomic particles. Okay. So the nuclear force is stronger than the electromagnetic repulsion force between the protons. Okay, so there is that attractive force, okay, and the neutrons help with that. So the neutrons actually will kind of break up some of that electromagnetic force. So it's not necessarily increasing the nuclear force, but it is decreasing the electromagnetic force. Okay, so the nuclear force also only works over very short distances. So you pretty much have to have the proton and the neutron touching in order for this to work. So as the nucleus gets larger, or if you have too many protons that are all close together and shoved in there, then the electromagnetic repulsion will actually overwhelm the nuclear force. And that's when you get the nucleus breaking apart. So there's all of this balance going on here. Okay, so you have the two positive charges of the two different protons. They're trying to force each other apart, but then you have your nuclear force, which is pulling them back together. And as long as you keep that electromagnetic force as low as it can be, then you're good. You can hold that atom together, that nucleus together. Okay, so when talking about the size of the atom, we talk about the radius. So radius of the atom depends on the size of the electron cloud. So the radius is from the center of the nucleus out to the furthest part of the electron cloud. Okay? So atomic radii are actually expressed in what's known as picometers. Tiny, 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 tiny. It's 10 to the negative 12 meters. Okay, is 1 picometer. So if we look at this, okay, a couple things you'll notice right away. The smaller radii are up and to the right. Larger are down and to the left. Okay. You're also going to see atomic radii increasing as you go down a column, and then increasing as you go from right to left across the periodic table. Now, a lot of the elements, once you're inside of the transition metals, they have very similar atomic radii, so on and so forth, but okay, general trend increases from right to left and then up to down. So your biggest atom is going to be in the bottom left corner, smallest will be in the top right corner. Okay, and these numbers show you the picometers, the radii in picometers of that element. Alright, so atomic number. Atoms of different elements have different number of protons. Okay, so by counting the number of protons in the nucleus of an atom, you can actually tell what element that atom is. Atoms of the same element will always have the same number of protons. So if you have 7 protons, you have nitrogen. If for whatever reason or however it happens, you lose a proton, that changes the element itself to carbon. Okay? If you lose a proton, you go down to 6, so you now are a carbon atom, or now have a carbon atom. Okay? The atomic number is shown as a capital Z. Again, don't ask me where these letters come from. It's like they used all the ones that made sense and then had all of these random ones left over that they just started assigning randomly to things. So the atomic number Z is the number of protons in each atom of that element. Okay, so atomic number, you put these on your moles. Okay, so they were the numbers that you had to have on your mole. The atomic number for, say, magnesium is 12, helium is 2, so on and so forth. So the periodic table organizes elements based on these atomic numbers. Okay, oxygen is 8, and that means that oxygen has 8 protons. Just so happens that oxygen also has 8 neutrons. Okay, and then whenever your atom is neutrally charged, so it does not have charge on it, it will have the same number of electrons as it does protons. Okay, so now we get into talking about isotopes. I'm sorry if you can hear my dog. He's got an itchy neck or chest or something. There we go. Hey, boys. Okay, isotopes. So isotopes are atoms of the same element that have different masses. You might think, okay, well, how can that be? So we know that they have to have the same number of protons because they are the same element, right? And remember, protons determine what element you have. They also have the same number of electrons, or they don't have to, but that doesn't really change much because electrons don't really have a mass. Okay? Potter is making himself comfortable on the couch next to me. You might hear a very dramatic sigh here in a little bit. Okay, then, so the only way that isotopes can actually have different masses while being the same element is by changing the number of neutrons. Because remember, neutrons have a mass but don't change the element. Okay, like protons would. So most elements actually consist of a mixture of different isotopes. And you have what's known as the mass number. Okay, so the mass number is the total number of protons and neutrons that make up the nucleus of an atom. Okay, now remember, it's just protons and neutrons. It does not include electrons because they don't really have mass, or at least enough to matter. Okay? Alright, so there are a couple different notations that we will use for isotopes. First up, we have the hyphen notation. So the mass number is written with a hyphen after the name of the element. So uranium-235, okay, carbon-12, carbon-14. You also have the nuclear symbol. So this is going to use the atomic symbol for the element, the number of protons, and the mass number. Sometimes they will leave off the number of protons because if you have the element, okay, if you know what the element is, you can look at your periodic table and find the number of protons. Okay, so for an example here, you have uranium, which is the U, and then on the bottom you can see the number of protons, which if you look at the periodic table, you will see that its atomic number is 92, so it has 92 protons. And then looking at the top number, to the 235, that is the protons and neutrons combined. Okay, so in order to figure out how many neutrons this atom of uranium has, you would take the 235, which is protons and neutrons together, and subtract out your protons. And then you would just be left with neutrons. Okay, so these are kind of some of how this all works out. Okay, so your mass number is shortened as a capital A. So it is your atomic number plus the number of neutrons. And then that is over your Z, which is your atomic number. And then you have your X, which is the chemical symbol for the element itself. Okay, so the number of neutrons, again, is found by subtracting the atomic number, so the number of protons, from the mass number. So here's your little formula for that. Mass number minus atomic number is your number of neutrons. So for an example, going back to our uranium, okay, we have 235, which is your protons and neutrons combined. And then if you subtract out your 92 protons, you end up with 143 neutrons. Okay, so uranium-235 has 92 protons, 143 neutrons. So how many neutrons does plutonium-239 have? Might want to pause it here to look up your plutonium and the number of protons plutonium has. Okay, so plutonium has 145 neutrons. How many protons, electrons, and neutrons are there in an atom of chlorine-37? So if you look at your periodic table, you'll see that chlorine has 17 protons. Okay, so then you take your 37, which is protons and neutrons together. You're going to subtract out your 17, so you end up with 20 neutrons. Okay, and then because there is not a charge on your chlorine atom, you have the same number of electrons as you do protons. So 17 protons, got that from the periodic table. Same number of electrons, 17, and then your 37 minus 17 to get your 20 neutrons. And that is this section.